Okay, so welcome back, and this is the first in the series of videos looking at the topic of optical isomerism. So your task for this week is to complete pages 1 to 10 of the notes and to make sure you've uploaded the little activity for Wednesday. But more about those details in the email we've sent out to you. So in this first little video, we're just going to be looking at structural isomers and also the first of the stereoisomers, geometric. So all this is revision. You've covered all these before, but we're just going to go back over them just to remind ourselves. So you're going to need your notes, and we're on page 1. Okay, so we're on page 1 of our notes, and as we've said, we want you to complete pages 1 to 10 this week. So we can divide isomers up into two broad groups: structural isomers and stereoisomers. So isomers are basically molecules which have the same molecular formula, so they have the same number of carbons, hydrogens, nitrogens and so on, but they have a different arrangement of the atoms in space, and that's why we call them isomers. So we're going to be looking at structural isomers first of all, and these can be subdivided into 3 different types: chain, position and functional group isomerism. So the first one we're going to look at the bottom of page 1 is the chain isomers. Now chain isomers basically have the same numbers of carbons and hydrogens. What differs is the carbon skeleton. So here I've got 4 carbon atoms in a straight line, and that's a straight chain isomer, and we call this one butane. But means 4, ane means I've got no carbon-carbon double bonds. Now I can take the same 4 carbons here and I can rearrange them to have the longest chain of a 3 and a methyl group here on this second carbon. So this makes this methyl propane because my longest chain now has 3, and this would be a branched molecule. Notice I don't need the number 2 on there because there's only one place for that methyl group to go. If the methyl group goes on this first carbon, it would be back to butane. So that's chain isomerism. So the second type of isomerism we can have is positional structural isomers. So this is where the functional group is in a different position on the carbon skeleton. So we've got the same carbon skeleton but a different position for the functional group. So for example, if again I take my 4 carbons, and I'm going to keep it nice and simple, I'm going to keep them in a straight chain, no branched molecule. If I have an OH group, I can put that OH group on this first carbon. This is carbon number 1. So this would be butan 1-ol. So butan because it's still got no carbon-carbon double bonds. But because it's got 4 carbons. 1 because the OH group is on the first carbon. And ol because it's an alcohol. I can have the same carbon skeleton. So I've still got 4 carbons. But this time my OH group is on the second carbon, not the first one. So it will be a secondary alcohol rather than a primary alcohol, which gives it slightly different chemical properties. So this is butan 2-ol. So that's my secondary alcohol. The last type of isomerism in this section is functional group, and they have quite different chemical properties. So again, I'm going to choose 4 carbons to keep it nice and consistent. This time, where if I put the double bond oxygen on the end of the molecule, so it's CO with the H, and again, I've got my 4 carbons, so that's butan al, because it's an aldehyde. I can have the same number of carbons and hydrogens, but this time I'm just putting the double bond oxygen on this middle carbon, and this time it's no longer an aldehyde, it's a ketone, so this is butan. And again, notice I don't need a number here because there's only one position for that double bond to go. So that double bond O has to be on the second carbon. Doesn't matter if it's on this carbon or this carbon, it would still be on the second carbon. So that's why I don't need a number for that one. So on to the second type of isomerism, which is stereoisomerism. And these have the same molecular formula and the same bonds present. However, there's a different 3D orientation of the atoms in space, which give them a specific type called stereoisomerism. Now, type 1 is geometric, otherwise known as EZ isomerism. And this is one, again, you studied when you did the alkenes notes. So I'm just going to go through this one. So here we've got black blobs, which represent carbon atoms, green, which represent chlorine, and my hydrogens here, denoted by the small white. So this molecule is called 1,2-dichloroethene. And they're both the same. They're both 1,2-dichloroethene. So they're both the same name. However, in this molecule, the two highest priority groups, which in this case are my chlorines, are on opposite sides to each other. So this one we call the E version. Here, the two highest priority groups are on the same side, excuse the German. So therefore we call this the Z1 version. Okay. Now, how do I decide which is the highest priority? Well, it's simply the atomic number. And here I have hydrogen and chlorine. Chlorine has a higher atomic number than hydrogen, so it has priority, and the same here. Now, it's not enough just to have the double bond. We need the double bond because it's providing us with restricted rotation, but that's not the only thing we need to have to show geometric isomerism. The second thing I have to have is that these two groups have to be different from each other, and these two groups have to be different from each other. If both of these are chlorines or both of these are hydrogens, it wouldn't work and you wouldn't get geometric isomerism. So the other characteristic is that each carbon of the carbon, double bond carbon, must have different groups, different atoms or different functional groups, or just they have to be different from each other. So these two can't be the same as each other, and these two can't be the same as each other. Same way here, these two you can see are different from each other, and these two are different from each other. Now, this helps us to explain things like why but1-ene does not show geometric isomerism. So if I draw but1-ene, I'm just going to do my C2H5 group up there, and my hydrogen here, and my hydrogen here. So I do have that double bond, that's going to help me, that's restricted rotation. I do have different groups here, so that's fine, so that works, but these two are the same. So it does not show geometry because the first carbon has, or the first carbon I should say, of carbon double bond carbon has two of the same groups, or two of the same atoms on there. Okay, so if we, on the other hand, we look at but2-ene, well, here we can see that if I draw this molecule out again, showing it orientated around the double bond, I have a different group here and a different group here. So these two are different from each other, these two are different from each other. So first of all, I have that carbon-carbon double bond. That gives me my restricted rotation. Notice we don't say there is no rotation. You can rotate technically around that pi bond system, but you would need to require a lot of energy to do that. So there's restricted rotation. And secondly, and most importantly, each of the carbons of the carbon double bond carbon has a different group on it. Okay, so these two are not the same, and these two are not the same as each other. Now, it's not only alkenes which show geometric isomerism, there are other molecules which can show geometric isomerism. Another one of these is something called transition metal complexes, which we'll study later on in the year. But the one you should be aware of as well is cyclic groups. So if I've got cyclohexane, so that's 6 carbons 5, 6 carbons in a ring. Now, if I have my bromo groups, my 1, 2 dibromo, I'm not going to draw the hydrogens on here, pointing up out of the circle, if you like. That's one version. That would be a same because they're on the same side, so that would be the Z version. If I rotated that bromine, or I put that bromine pointing downwards, then it would be a different version. It's quite difficult to see this on a 3-dimensional 2D paper, so you might just need to sort of try and have a think about that one. But you can't rotate one version into the other because this time it's the ring which provides restricted rotation. In this example it was a double bond. In this example it's the ring. So you have ring structure which restricts rotation. So I can't rotate it. And I have two adjacent carbons, I should say, with different groups on them. So this one would have a hydrogen and this one would have a hydrogen. Now if I wanted to swap the place between that bromine and that hydrogen, I would have to twist this group around, and I can't twist it around because that would break the ring. So there is another version where the bromine is here, if you like, and the hydrogen is here, and therefore my two bromines are on opposite sides, and therefore you've got your E version. So that's geometric isomerism. Okay, so that finishes this section of the notes looking back at structural isomers and the first of the stereoisomers, geometric. In the next video, we're going to move on and look at the new type of isomerism, optical isomerism. So I'll speak to you later. Take care. Bye bye.